So, ladies and gentlemen, thank you very much for coming to this exciting session. As I said, I felt that it would be nice that I just give an intro to topological photonics, and if Supra and anyone else who's co-host, if you could let people in, awesome. Thank you. So, introduction to topological photonics. And again, it's going to be super pedagogical. So we're going to go through like very, very basics. And if you get bored, go and get a sandwich. So the goal of this lecture, or maybe a couple of them, is to go over basic models of topology. Let's say quantum Hall model, Valley quantum Hall model, photonic analog of them, and the physical observables that are relevant to photonic systems. Okay, so that's kind of the course plan. Now let's step back. What do we mean by topology? So topology, very general, and I have shared the notes. If you don't have them, please ask other folks to share them. Is it subject that has to do with the general form of your system and not the specific of the system, meaning that usually people give an example of a donut and a coffee cup, that they're topologically the same. You can deform them from one to another without breaking them, so they're topologically identical. But I have been using this analogy, the analogy of an island. Regardless of the shape of this island, you always call it an island, right? They're all topologically similar to each other. That's why we have one word for it. If it's heart shape, if it's sphere, not a sphere, if it's a disk, if it's a rectangle, it's always that. But if it's an island that is connected to the mainland, so it's the bulk, for example, then you call it peninsula. That it means basically it's like almost an island. It is not an island because it's connected to the land. So more specifically, if you start from here and then swim around the island, you can swim either clockwise, integer number of times. You can swim like this, you can swim like that, or you can go backwards. You can go in the opposite direction, integer number of times, and that's always an integer. That can be always positive or negative. But if you want to do the same thing for a peninsula, if you want to go around it, you cannot do it. So that number becomes 0. So they are topologically distinct. So I have actually come up with some integer that distinguishes an island and a peninsula. So now the whole point of topology in physics is that if I can associate a physical observable, what is a physical observable? Like transmission, conduction, resistance, whatever, to one of these integers, then that integer would be robust to small deformations. Because if I deform my peninsula to this, or if I deform my island to this, it does not matter. That integer that I have introduced over here would remain an integer. And that's the whole point of this classical topology. So this was very, very classical. If you think of now a quantum system, let's think of a single particle wave function, let's say psi of x and y in a two-dimensional system. This can be a wave function of an electron in a two-dimensional system. This can be a wave function of a photon, solution of the Maxwell's equation in 2 dimension. This I can write it also in the polar coordinate. So not only it would have, I can write it in terms of x and y. I can also write it in terms of r and theta. So it has an amplitude, this guy, but also it has some function as has a phase. Sorry, it has a functional dependence on the phase. So the phase of this guy can have interesting points. In particular, if let's say if you're solving Max's equation in a two-dimensional system, you get solutions e to the im theta when this theta is just this theta. M can be plus or minus. And those basically tell you how many times your wave function winds when you go around the zero of your system. So if you have a vortex state in particular, the M will tell you how many times that function winds around itself, right? So that's the phase winding. So now it's actually, this is the kind of the wave analog of what we had over here. And this M, this integer, cannot change by a fraction as long as your system, your manifold is simply connected. M should be always an integer. So when you take E and M, as long as you solve Max's equation for a system that everywhere is accessible, it's fine. If you solve a system for something like this, an edge, then M does not have to be an integer. Anyone remembers this from Jackson or similar? So the quantization of M really comes from the fact that you have everywhere access to the space. If you take part of the space out, then this does not have to be an integer. So now, when you have such a wave function, then you can define the circulation, basically that phase, this guy, around some closed loop. So I have my wave function, it winds around itself. I define a loop, I take a loop, I call it C, and I add the phase of this wave function when I go around this loop. I evaluate derivative of delta, that delta L, and this guy, if everything is nice and well defined, then if you use the Stokes theorem, you can write it as a curl of this dot ds. So you can turn this loop integral into the surface integral over this area. And we have another person. And if this is well defined everywhere, then this is always zero. But if phi is singular, sorry, this is not phi, this should be the psi. Then this is singular, and the number of vortices that you have in the system would tell you that would give you the circulation. So this, you had it in fluid mechanics, you can have it in optics, you can have it in anywhere. So there are 2 points: that this guy will no longer be zero, it will be n being an integer. And then the second property is that your wave function should be zero. So this guy should go to zero at some point. Okay. So basically this vortex solution that you had in E&M or in quantum mechanics, those are topological manifestation. This phase winding that you have over them, you can not get rid of them. So here we were just talking about a wave function in real space in x and y. So our two-dimensional system was x and y. But this idea can be generalized to any parameter or any space. So now instead of x and y, you can have px and py. Now these are, let's say, momentum in the Brillouin zone for a two-dimensional system, or some general parameter theta x and theta y. It doesn't have to be a real space dimension. It can be any two parameters that you can change in the system. So as long as you have these kind of constructions, then you can have the wave function in that space, and then it can have phase winding. So a very high level example of that is a photonic crystal. So take a photonic crystal. It's a photonic crystal that is bipartite. So when you write the tight binding model for this, you will get two bands. So there's one band over here and then the other band over here. And then you have energy as a function of ky and kx. Right. And many of you have solved this maybe. So depending on where you are in the Brillouin zone, you might have been concentrated more on the A sublattice or the B sublattice. So this is the energy, this is the eigenvalues of the solution to this bipartite system. These are the eigen states of the system. So if, let's say in this position, most of my wave function is concentrated on the A sublattice, then this unit vector will be pointing up. If I'm in somewhere in the Brillouin zone that where my wave function is more concentrated than B, I will be over here. If it's something in between, it's something over here. Okay. So this you have seen in solving any tight binding model that has bipartite situation. So this is something like a general formula would be something like that. Ji plus a dagger I, let's say vi, and then v prime I, b dagger vi. This is a second quantized form, but you can also have a linear and first quantized. There's a second quantized formalism, but you can also write a wave equation for this. Now, most of the physics that we know in photonic crystal can be described by this guy. Basically, how energy or frequency changes as a function of kx and ky, how energy depends on different momenta in the system. So in particular, if the system is gapped, it means that at some value of kx and ky, my E is gapped. I don't have any energy state. Or if I'm interested in the group velocity dispersion or higher orders of that, then I have to take the derivative of this E with respect to K. So the first derivative, second derivative, third derivative, etc. So just knowing how eigenvalues change as a function of kx and ky, I get a lot of information, and that was the whole deal until maybe 10 years ago. So you have a band structure, and then you get all the information from the band structure. But as we saw here, we can also look how the wave function changes as we go and explore the Brillouin zone. So how the wave function of our system changes when I go from one part of the Brillouin zone to another part of the Brillouin zone. In particular, if I go around this Brillouin zone and I come back, I should come back to the same state. And then if I track it over here, maybe we start over here, we go over here, we go somewhere over here, and we come back. Or maybe we go all the way over here and then we come back. And then you can associate whether you have completely inverted your unit vector or you have always remained in some part. You can associate a integer to that, whether when you're exploring the Brillouin zone, whether you are exploring just one part of this Brillouin zone or the whole part of the Brillouin zone. I'm not being very specific here, but I just want to give you a flavor of how things are going. Now we are looking at the global properties of my wave function. I'm not interested in the local properties of this thing. I really care about how the wave function changes as I go and wander around the Brillouin zone. Now, if I can associate some observable again to how these unit vector, whether it wraps around the whole block sphere or not, then that would be an integer and that would be robust against deformation of the band structure. So if I mess up my band structure is a little bit, this energy state as a function of the momenta would change, but then it not change whether I have wrapped around the Brillouin zone once or twice, etc. And those properties will be robust. Any questions so far? Just on the general.
I do have a question. How much is a little bit in terms of the formation? Is there a
too fast, too trivial? You should let me know.
Can you hear me?
Okay, so now with this very, very general thing, we come back to this intuitive picture. Yes.
Okay, can you hear me?
Just unmute yourself and ask questions. You don't need to raise your hand.
Can you hear me? Can you hear me, Mohammed?
I can hear you, but it seems Mohammed probably cannot hear you.
Okay.
Hello? Yeah, like Daniel was asking a question.
Yeah.
Oh, very interesting. Hello?
Can you hear me now?
Yeah, I can hear you.
Okay. Now my question was related to the about the robustness against small perturbations. So how small is a small perturbation? Is there a limit for that, or what is the physical condition that defines how big the perturbation can be?
Very good question. Yes, it's not unbounded. There is some limit to that. In particular, in the language of here, my perturbation, not here over here, my perturbation should not close any gap. So if I have a band over here and I have a band over here, this deformation can deform these this top band or the bottom band, but it should not close the band gap. Over here, more intuitively over here, my deformation should not be so much that will take me from one integer to another integer. We will be more specific about this, but indeed I can add a perturbation so strong that it would take me from one of these integers to another integer. So there is some there is some limit to the amount of perturbation that you put in the system. Okay.
Mohammed, can I also ask a question?
Sure.
So when you're going around in a circle in the Brillouin zone, as you have just shown, like, are you saying that it is possible to go down into the lower band, or because your vector is pointing to B and then back to A, right?
So sometimes I go all the way to the B, sometimes I stay on the top. So depending on whether it's topologically trivial or not trivial, when I go around the whole Brillouin zone, so when I explore Kx and Ky and look at from 0 to 2 pi over here and 0 to 2 pi here, sometimes I wrap around the whole Brillouin zone, sometimes I only stay at the top.
I mean, wrap around the entire band, right?
So you see this wave vector, we will be more specific about this. This is just picture, but I want to answer you right now. So this unit vector is okay. Just give me a second. Okay, now it's good. No audio. This unit vector is n as a function of kx and ky. So for any value of kx and ky, and also the band. So I have, like, let's say, the top band and the bottom. So this alpha can be alpha up or alpha down. Very good?
Good.
Okay. So now when I go and change kx and ky, this unit vector can start to move. Sometimes it would wrap around this whole unit sphere. Sometimes it stays only at the top.
For each label, up and down.
Or each of these bands, yes.
Okay, now I got it.
Yeah.
Thanks.
Yeah, and then we will be more specific where we put really a model, and then you will see how this unit vector changes as a function of kx and ky.
Got it.
Okay, no question? Okay, so now let's start with the kind of the mother of all topological models in physics, and that's quantum Hall effect, which is a very simple and yet beautiful problem. It's two-dimensional electrons in the presence of in a perpendicular magnetic field. So I have a two-dimensional system, I have a perpendicular magnetic field, and I would like to understand the physics of this. So first, look at we look at this problem from three different levels: classical, semi-classical, and quantum. Let's just do classical. So in the classical picture, what do you have? You have an electron, and you will go through cyclotron motion because you have F is equal to QV cross P. And then you learned in the first year physics is that you would go through a cyclotron motion, either in this direction or the opposite direction, depending on the sign of your charge, right? So it will go through some cyclotron motion with radius r. And then, so m dv over t is equal to q v cross p. And then this will, if it's a circular motion, then the centrifugal force is equal to the charge of the particle. Now I take E for Q, you can just put Q. V is just omega R, and B is just this, okay? So now you see that R cancels from both sides, and then W, omega, sorry, will be EB over M, right? This is called cyclotron motion, cyclotron frequency, okay? Or cyclotron energy if I put an H bar in front of it. So from this picture, you see that R is not bounded. R can be anything you want, right? But the frequency of this is fixed, and that's just given by charge M and B. Now from from semi-classical picture, like Bohr-Sommerfeld or any kind of picture you want, this wave function of the electron should also wind an integer number. In particular, if you look at P dot Q in Bohr-Sommerfeld, it should be H bar times an integer. Another approach that I usually like is that I want to see how small these orbitals can be allowed by quantum mechanics. So if I assume the smallest orbital, what would be the value of the R that I get? Because I know from Heisenberg uncertainty, X and P uncertainty cannot be smaller than H bar. So let's take that the smallest one should be of the order of H bar. So what is X? For the X, I just assume that that's the radius. And for the P, that would be omega. So it would be mv, and v is just omega r. So this basically tells me that m omega r squared should be equal to h bar. The smallest orbital that I can make is this. So then r should be h bar or m omega. Okay, omega c, because now we have assumed that this is a cyclotron motion. And if I write it in terms of magnetic field, it would be this, if I replace omega from here. So this tells me that your once you enter quantum mechanics, Heisenberg does not allow you to have orbitals with radius smaller than r. And this we will call magnetic length. Magnetic length. Sounds good. Now the question is how many of these orbitals I can pack in a system. So let's assume that this is the smallest radius that I can make. So this is LB. So this is LB, 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 LB. So the area of each of them is pi LB squared. I'm not keeping track of 2's, etc. So we will be off by these values. So if my system, let's say my system is Lx times Ly, Ly being in this direction, Lx being in this direction, if the total system size is this, then how many orbitals I can pack in the system? It would be A divided by pi LB squared. Number of small orbitals, right? And now if you work this out, so this A is A, but then this LB squared would give me this. So I have to put the opposite of that. So this is EB, A divided by H, maybe some factors of pi, etc. But B times A is the total magnetic flux in the system, right? So that will be the total magnetic flux in the system, and H bar by some C would give me the quantum of magnetic flux. So this will be basically the total magnetic flux in the system divided by the quantum of magnetic flux, basically the number of magnetic flux that you have put in the system. So with this very semi-classical analysis, you see that the lowest, you kind of get a feeling that the lowest state in the system is n phi fold degenerate, and n phi being the number of magnetic flux. Sounds good? Okay. So now we want to see what happens in the quantum regime in a second, but just what happens over here. I just want to show it. So you will get n phi degeneracy in each of these levels, and each of them is separated by h bar omega c, the one that we had even from the classical picture, that we would h bar. So that from the semi-classical point of view, we expect some spectrum like this. Now, before going to the full quantum version, let's review what quantum Hall effect is. Quantum Hall effect, and this is integer quantum Hall effect. So there is no interaction. So there is no interaction. It's just single particle physics. Actually, throughout this whole lectures, we don't go and include any interaction. We can do that later, but that's not the subject. So what is quantum Hall effect? Quantum Hall effect is that you have a two-dimensional electron gas. You look at the voltage and current in transverse direction. And again, from this semi-classical picture that we just described, is that in the middle you have cyclotron motion if you have a magnetic field. So these electrons cannot contribute to the conductance because they're localized. But then if the electrons happen to be at the edge of the system, then they cannot complete their cyclotron motion, so they start to skip around the edge of the system. And they can contribute to the transverse conduction. So these guys, the bulk ones, don't contribute to the conduction. Only these ones would contribute to the conduction. Now, I didn't go into the details of it. We will again come back and make it clearer and clearer. As you realize, the lectures are like this. We build layers and make it more precise as we go. But I would like to connect this picture to the swimmer's picture, to the swimmer around the edge. So if all the electrons in the bulk are localized and only the edge are contributing to the conductance, then you immediately see that this is topologically protected, because if I put some disorder at the edge of the system, or if I just chip it, then instead of this, my electrons would hop around this edge and then continues its way. So as long as I have a two-dimensional system that has some edge, that's fine. The electron will find that edge and will go through it. But if I change the topology of the system, let's say imagine instead of having square like this, I have a square that has a bunch of holes in it. Then not only I have this edge, but I also have these edges. So the electrons not only can go around the edge of the system like this, but it can go around the edge of the system like that, it can go around the edge of the system like that, etc., etc. So if I take a material and punch a hole in the middle, would it become immediately topologically sensitive or not? This is related to Daniel's question. With this classical picture, we can already answer this. Any taker? My question is the following: is that I take a two-dimensional system, and I create a very small hole, like over here and over here and over here. Does that change my conductance?
It should not.
Why not?
It would not contribute to the edge currents.
Yes, because
depends how close it is to the edge. If it can scatter to the edge.
Exactly. If these guys, if the states around these guys are far away from the edge states and they don't tunnel, the distance is far and they don't tunnel, it doesn't matter. Because you can ask, I have asked the same question from me, is a rectangle and a ribbon, they're topologically the same? So a ribbon is like a very large ribbon, a rectangle is something like this, or a square, or a disk, etc. They're all topologically the same. But if I really stretch this ribbon, at some point I will become one-dimensional system. So at what point you say that it's one-dimensional? We are not doing math, we are doing physics here. So what's the length scale at which things go bad? That the thing is no longer 2D and it's 1D. What's the answer to that?
Comparable to the cyclotron radius. Like some
Cyclotron radius doesn't exist.
or
Magnetic length, no?
magnetic length. Sorry. Yeah. Sorry.
Very good. So as long as the width of the system is larger than LB, then these guys and these guys don't talk to each other. So I'm fine and I can call it a two-dimensional system. So you see, already with this picture, you can explain a lot of things that is happening, like in terms of like the system size, the shape, etc., etc. So this LB is a very good intuitive parameter to keep in mind. Okay, so now the quantum Hall effect was that when people looked at this V over I, so V, so this is V, this is Y, and this is X. So when von Klitzing measured this, rho XY, which is equal to rho XY, in 2D actually that is the case, that the transverse resistivity and resistance are the same thing, and looked at it as a function of as a function of magnetic field, then from a classical point of view, you should expect that it would be a line and then rho xx. So this is, sorry, I just rho xy, then rho xx. So this, from the root formula, you get me squared n tau, and then this one from again root formula, you get b divided by ne. But when it was measured, they realized that it's actually not like this. It has steps. Sorry. So this n is the density of electrons over here. Sorry, because messing with the numbers. And then this guy, instead of being just flat, it would have peaks in between these plateaus. So you would see steps instead of a straight line for rho xx, rho xy, the transverse conductance, and then for rho xx, the longitudinal conductance or resistance. You would see that you have a bunch of peaks, and at some point in the plateaus, it's zero. Okay. So now this basically semi-classically can be described by the fact that your conductance is not through the bulk, it's basically just through the edge of the system. And the number of channels that you have, it's either one channel or two channel or three channel, and that would be the height of these steps. So, okay, enough of semi-classical picture. Now let's look at the full quantum picture. In a full quantum picture, I have to look at the Hamiltonian of the system. So it's a bunch of electrons in 2D, so it's just p squared. But now in the presence of magnetic field, I have to do minimal coupling, couple it to the electromagnetic field. Now I write it both in the x direction and the y direction. Right? Now A, in order to describe a uniform magnetic field in the z direction, can take many forms because it's a gauge field. So I can write many different forms of A that gives me the same magnetic field. Either I can have equal weight both in the x and y direction. This is usually called the symmetric gauge. Or I can put all of it in one direction. X, and that is called the Landau gauge. If you calculate in either case this curl of A, it would give you B in the z hat direction. You can come up with other gauges, but the physics in the end should be invariant depending, regardless of your gauge choice. Okay. So now let's keep that in mind. So AX can take this form, AY can take this form. But now let's do a trick. Let's look at this guy, and let's call this pi x and call this pi y. And what we learned in quantum mechanics is that whenever you identify something as an operator, you look at the commutators between them. So what is the commutator between pi x and pi y? Any idea?
The magnetic field?
Yes, so but why? Because you see, px is proportional to derivative of x. Py is proportional to derivative of y, right? So then pi x is some pi x, apart from i's and things, then I will have this, sorry, and then pi y e y. Let's take the, let's say, symmetric gauge, or no, you don't even need to take the symmetric gauge. So this guy, when you look at the commutator of this and this is 0, but when I look at the commutator of this and this, it will give me the derivative of ay with respect to ax. And when I look at this term, and this term, it will give me minus sign, because now I look into the commutator. It will give me now derivative of ax with respect to y. And then again, this one and this one, they commute with each other because they're just two functions of positions, either in the x or in the y direction. So this is just nothing but the curl of A in the z direction, which we took to be just a uniform magnetic field. So specifically, if you work out the math, the commutator of pi x and pi y is nothing but minus I e h bar b. So it's a constant times I. And it immediately reminds us of x and p, right? So the commutator of pi x and pi y are very similar to position and momentum. So then in your head, you can look at this Hamiltonian and I said, this is nothing but just 1 over 2m, some x squared plus some p squared, right? And that's the Hamiltonian of a harmonic oscillator, right? And a Hamiltonian of a harmonic oscillator gives you harmonic ladder. So we have already solved the problem. In particular, I can define ladder operator similar to the ladder operator in a harmonic oscillator, that you take px minus ipy plus some constant in front, and then a dagger in a similar fashion. I chose these prefactors such that now a and a dagger would become beautiful bosonic operators. So this Hamiltonian that we knew it will be a harmonic oscillator. Now again, this will be a harmonic oscillator. And if you work out the math, you beautifully recover that this omega, the energy of the frequency of the harmonic oscillator, is nothing but the cyclotron frequency. So what does that mean? It means the system is harmonically spaced. Each of them is h bar omega c. And that's it. So that will be, let's say, n0, n1, n2, n3, etc. So the energy of this one would be 1/2 h bar omega c, 3/2 h bar omega c, 5/2 h bar omega c. So far we just realized that they are equidistant. It's like a harmonic oscillator. But if you recall, we had also this degeneracy that we talked about. So how can we find this degeneracy in this quantum description? Before doing that, is there a question? So again, we're dealing with quantum mechanical problem. I need to identify some operators that commute with the Hamiltonian. And the Hamiltonian, it means that they can give me actually degeneracy. I can go from one state to another state without changing the energy of the system. So this is actually very similar to what we did. So instead of now pi x and pi y that we defined as px plus e ax and py plus e ay, I choose pi x tilde to be pi x minus ex and pi y px minus ay. And I stick to the symmetric gauge. Because now over here it was actually gauge invariant. Regardless of the gauge that you choose, you always get magnetic field over here because it is just a gauge invariant quantity. But for these guys, when we look at the commutator, we have to choose a gauge, and I choose to be in the symmetric gauge. So you can do the same math. You can look at the commutator of pi x and pi y, and then you realize that it is again very similar to the x and p, the position and momentum in quantum mechanics. And this pi x commutes with the other guy. This pi x would commute with all the other ones. So all the commutators are 0. They just, pi x and pi y would give me I, pi x tilde, pi y tilde would give me I, but all of the other ones would be 0. So now again, since I have these two operators, I can define a ladder operator. Now I call them B, which would be, I don't write the proportionality constant to save time. This would be plus I, y, and then B dagger proportional to pi x minus pi y. Okay, so these two are ladder operators. Again, if I look at their commutator, it will be bosonic, etc., etc. So now, what is important about these pi x, these tilde ones, or now I call them B, so I don't need to repeat this tilde every time that I talk. Now, what is amazing about this B operator and then B dagger operator is that they commute with my Hamiltonian. What does that mean? It means that it does not change the energy of the system if I apply them to my state. So imagine that I have one state over here. I apply the B operator, I will get another state. These are these n phi states that we would like to find. So if I apply that, if I apply a B dagger, or if I apply a B dagger, it does not change the Hamiltonian of the system, but it changes the state of my system. So again, remember that a harmonic oscillator could be written in the terms of Fock state n. N can be 0, 1, etc. So that could be n. But now I have two kind of harmonic oscillator, which one of them has energy 0. So it will be something like that. So the any general Fock states like this is the application of A dagger n times and B dagger m times, and some normalization that we usually have over the vacuum. Okay. I have not told you what the form of these wave functions are, but just knowing the harmonic oscillator, we just realized that these A operators, when I apply them, it will change my energy by h bar omega c. And when I apply B, they don't change my energy because B operators commute with Hamiltonian, but it would give me a different state. So in order to characterize, in order to index my Hilbert space, I need two numbers. One is n, one is m. N will change the energy of the system from this ladder to this ladder to this ladder. M would change the state of my system, but stays in the same manifold. Sounds good? So I did not use anything more than a harmonic oscillator to find the spectrum of the system. Now, if you ask me what is the form of the wave function, then I have to say that in the manifold, in the ground state manifold, I have to put n equal to 0, and m can be any number. Again, if you go back to Griffiths, it's the same way that we get the wave function of harmonic oscillator. This guy, the annihilation operator over the ground state of the system, should give me 0, right? So I can use the same thing. What is the form of A? The form of A is given by this expression over here. So I just plug it back. So it's a long form, and I don't go through the details of it. I leave the notes in case you want to follow that. But the idea is that you have some derivatives over here. Sorry, some derivatives of x over here, some derivatives of y over here, and this A, when it applies on this, it should give me 0. So if I write it in the complex basis, so z and z bar are x plus minus iy. If I'm interested in the form of the wave function, here it was in the second quantized form, I was not interested in the form of the wave function. But if you're interested in the spatial form of the wave function, you have to do this calculation. So you replace A has some form, and I suggest that you go through it, and if you have questions, get back to me. You have a question? Oh, thank you. Yeah. So this guy should be 0. So by solving this, you already get some idea of the form of the wave function. So this will be psi of the lowest Landau level in terms of z and z bar. I switch from x and y to z and z bar. So you have to do a little bit of acrobatics, etc., and then you will find all the wave functions of the system. I skipped the derivation. This is not the only way to find the wave functions. I just wanted to show you a way. Now I write the form for the wave functions in the lowest Landau level. It's proportional to z over lb m e z squared over 4lb squared. Okay, this is really the results that I wanted. Okay, so what are the interesting things already? So you see there is one, yes, Daniel. Hey, Daniel? Hello? No, okay. I cannot hear you. So there is one, as you see, there is only one length scale in the system, and that's LB. I cannot hear you. No. Okay.
Hey, Mohammed, in the meantime, I have a quick question.
Yeah.
Is there some quick argument you can make that, okay, we introduce some new pi operators and get this M quantum number? Some kind of convenient completeness argument here, that would tell us, oh, we need to consider, well, we knew about the degeneracy semi-classically, but is there any way we can see that there's not more degeneracy here in this picture?
So this I didn't go through. Then you have to apply this B dagger until you run out of possibility, basically. You start with the ground state 0, 0, and then you apply B dagger, but then once you apply it n 5 times, you run out of possibility I'm not aware of a very intuitive picture. Why? I don't recall off the top of my head. If anyone has, please let me know. But that's the idea, that you start with the lowest one, and if you apply this B dagger n phi times, then you don't have any more possibility, basically.
So do you go to 0, or does it annihilate the the state, or circulate back to the ground state?
It goes back to the initial state, as far as I remember. Yeah.
So it's basically something that's circulating on. Okay.
Yeah, very good question. Yeah, I don't remember actually this. Yeah. The another way that people argue is not through this operator one, is that they really solve the wave function, this wave function from the beginning. There's quantum mechanics 101. You have a magnetic field. You solve the Schrödinger equation instead of this operator valued. And over there, you run out of space. You basically have a two-dimensional system. You find the states, and they are localized around some regions. Then at some point, you just reach the other edge of the system, and then that would give you the quantization. And that is the Landau problem. Landau spectrum or Landau levels, etc. I did not want to do that because that's usually the way that it's done in the books, and you can kind of look it up. But that's, if Chris, that answers your question. If I don't want to do this operator, you can just go and solve the Schrödinger equation, and then you will see that you hit the wall. You cannot go further than that. Okay.
Thank you.
Sure. The reason I like the symmetric gauge will become obvious in a second. And that's the following, is that these are the wave functions of the lowest Landau level. So this is the lowest, lowest Landau level. If I plot them, as a function of in the 2D plane, they will be something like this. Sorry for my bad drawing. So this is, so if you look at it from the side, the first one is something like this. The second one is something like this. The third one is something like this. The fourth one is something like this. So this is, let's say, the origin, and this is R. So they have the support just over here. Basically, it's a bunch of rings. So, and then those wave functions, those are well-defined wave functions. I call them psi of m. Psi of m as a function of z. So these are the wave functions of these guys. And now you can ask, what's the expectation value of r for them? Or what's the radius? The average radius of them. So this is the radius of m for orbital m is given by 2m lb. So if you increase m, then the radius of this one, so if this is the first one, if it would be lb, and then the second one would be square root 2 lb, etc., etc. Now, each of these orbitals should accommodate a single magnetic flux. Because remember, this picture and the previous picture that we had, that we pack the system with LB should be equivalent to each other. The states are degenerate, So you can take any superposition you want. You can make a superposition like this, and then form orbitals like this, or you can take the same system and then represent it like this. It does not matter. All these orbitals have the same energy, so I can take any superposition of them. On the top, we're looking at this superposition. Over here, I'm looking at this kind of superposition. But remember, if I have m orbitals in each of them and phi orbital in each of them, over here, each of them would carry one quantum of magnetic flux. So over here, again, each of these guys should accommodate one quantum of magnetic flux. So if its radius is becoming larger and larger, then its thickness should become smaller and smaller because its area should be fixed. So then, in particular, if the thickness of these things should go, the width of them should go as LB divided by square root m. Now, again, going back to kind of Chris's question in terms of like size. Is there a question? Here, if I
Can you hear me, Mohammed?
Yes, I can hear
okay,
you.
finally. So far we have talked about the Landau levels, so the oscillator, the harmonic oscillator, but the explanation for the or the physics of the edge is not included yet, right?
Yes, yes.
Oh, okay then. So
Yeah.
it's only in the bulk, correct?
No. It's in the bulk, and actually,
Okay.
I will get to it right now.
Okay,
Yeah.
okay. Thank you.
So now, you see that I'm being a little bit sloppy. Can you hear me now? Can you
Yes.
hear me?
Yeah.
Okay. It automatically went to my Bluetooth. That's why. So I was a little bit sloppy with the boundary conditions. We were just over here. I kind of assumed a rectangular system. Over here, I should assume a disk. So I start with these orbitals and I pack them one after another. And at some point, the radius of these orbitals cannot exceed the radius of the system. So M max, it should be in such a way that Rm max should be equal to R, the radius of the system. So 2m max LB. So if now the area of the system, what is the area of the system? Is pi R squared. It would be pi 2m max LB squared. So then m max, pi and pi will cancel each other. It would be LB squared. Sorry, it would be R squared divided by LB squared. So the maximum number of orbitals, this is related to Chris's question, but I will finesse that. The maximum number of orbitals that I can put in the system is the system area divided by the magnetic length squared. Didn't we have that? It's the same thing. It's just over there I assumed a rectangle. Here I'm assuming a disk. So this is again the total number of magnetic flux in the system. Now, if the answer that I gave to Chris was for an infinite system or a system on a closed boundary condition, so you can ask, what if I'm not on a disk? If I'm on a torus on a closed boundary condition, then if I start making these b orbitals, if these b orbitals take me from one to the other, I won't go to the edge of the system because the system does not have edge, and I will come back to the same state. That's why I said to Xinhuan that you will come back to the same state. But the form of them I don't recall, because on the torus, the form of these wave function is no longer this. This is for a disk. And on a torus, when it's a closed boundary condition, it's Jacobi theta function. They're very nasty, but people have written their form. Okay, so
Can I ask a question? So it seems that the wave function is actually dependent on the origin that you're choosing. Because right, you write z, and z is just x plus iy, and x is the x distance from the origin, but then it should not be dependent on the origin, right? That you choose.
Anyone wants to answer this question? So I will answer it. So, so I chose my gauge. You see, I had this gauge freedom over here and over here. I chose the gauge to be the symmetric gauge. So I actually already picked an origin for the system.
Oh, okay. Okay.
But you're right. In the end, at the end of the day, when I measure some physical observable, it should not depend on this gauge choice, and it should not depend on this origin, etc. Because my Hamiltonian was did not care about the origin of the system, did not have any origin. So these wave functions I could have. That's why I said you could do the wave functions like this, or you can do the wave functions like that.
Okay. So that means that sometimes the wave function is not something that's really physical. The correlations are actually something that's physical.
Yes, I can indeed. In the end, when I want to, let's say, look at some physical observable, let's say conductance, then I have to sum over the contribution of all states in that specific energy state.
Okay.
Say,
okay.
So, for example, over here, let's say in a quantum Hall system, you put your Fermi level over here. Means that at zero temperature, all the states, let's take a Fermi level, let's say over here, then all the states below the Fermi level should be filled up. And then I have to look at the contribution of all these states to the transport, to the excitation, optical response, etc., etc. Any other question? So now going back to Daniel's question, what happened to the edge states? So here, if you assume that the system is a disk and it does not have any confinement at the edge of the system, it looks like that I have these orbitals, one after another, and then I hit the edge, and that's pretty much it. So you can call any of these guys, any of these states as the edge state of the system. Now, if I put the system in a confining potential in a harmonic trap that is very, very shallow, then you remember that in the absence of confinement, I had degeneracy and phi degeneracy for each of these Landau levels. Now I put it in a harmonic trap of the form 1 over just something VR proportional to R squared, right? Then my Landau level would be like this. So each of them will be n phi degenerate. Is no longer degenerate, but I have still n phi, but now I have a confined potential. So now the degeneracy is lifted, but each band has n phi states. And now you can call this is an edge state, that this is an edge state because it has a different energy than this guy, than this guy, than this guy. But what is important is that imagine that the system is azimuthal symmetry, it has cylindrical symmetry. Then the form of this wave function is what? Is a guy that goes around the system. What is the form of the wave function? I have it over here. It is proportional to z to the m. What is z to the m? It's r to the m e to the I theta m. It is exactly similar to the form of the wave function that I advertised in the beginning of the talk, that it's a guy that winds by m times. The guy next door, m minus 1, is r m minus 1 e to the I m minus 1. So this guy winds m times, this guy winds m minus times. As long as I don't mess them up too much, I cannot go from m to m minus 1 adiabatically, correct? Because one of them is winding m times, the phase of this wave function winds m times. The phase of this guy winds by m minus time, so they cannot just switch immediately. So this means that if I add some impurity at the edge of the system, then my wave function should accommodate this extra bump and then goes around this impurity, such that it would remain single valued. It may not have the cylindrical symmetry anymore because you have put your finger on one part of the disk and not the rest of the disk, so you have broken the cylindrical symmetry. But nevertheless, if I look at the wave function phase and I go around it and I come back, I get 2 pi, 4 pi, 6 pi, etc. It should be an integer times 2 pi because the phase of my photonic wave function or electronic wave function should be single valued. So the whole point of this topological protection for these systems is that since the wave function should be single valued, then if I add this phase around this loop, if I measure this circulation, it should always give me an integer times 2 pi. So I put my finger over here, the wave function would deform to accommodate that, and then it would remain. But if I push it further, then I may actually hop from this m to m minus 1. Is it now more clear since the beginning of the lecture? Any question?
So for a given n, I have only one m that contributes to the edge current. Is that so? Like, which is the maximum m?
So no. So in a quantum Hall effect, actually, what happens is that if you put your Fermi level over here, then you will have this edge state, and this edge state. So each band would contribute one of them. So then that's why you get n e squared over h for sigma xy. So this n would be number of Landau levels that the Fermi level is above that. So each Landau level will contribute to one edge state, and if my Fermi level is over here at the blue, so this is EF, then I should sum over all the contributions from the bands.
So if my Fermi level is low enough, I could have only one individual state in the contributing to the conduction in the edge.
Correct.
Oh. Okay.
Yeah. And this is a very cartoon picture of integer quantum Hall. I did not add disorder in the system. one actually have to add disorder into the system to get a more accurate picture. But for our purpose, I think that is enough.
So in the symmetric gauge wave function picture, those circular concentric rings, so these, each circle represents like one of these Landau levels. And if I'm not wrong, the number of times you go around each circle, the Chern number gives you this, like the degeneracy in the each Landau level, right? Am I right?
I did not talk about the Chern number yet.
Okay, but is that true? What's the degeneracy in each Landau level? Is that the number of times you winding?
So, okay, so let's clarify this. So first of all, these are called Landau levels, okay, each of these guys.
Yes.
And these guys are called Landau, say, orbits. Okay, so these are different orbitals. Now, when I want to talk about the Chern number, and we will come back to this Chern number business, is that I have to specify where my energy is, and then calculate the Chern number for a band. So I have to sum over all these guys.
Okay.
And it turns out the Chern number of that is equal to 1 for the Landau problem.
But in
this M that we have over here,
right,
is not really connected to the Chern number. Is the winding of the state is that's why I'm doing this wiggily. That this is just how many times your phase is winding. It's a system size dependent quantity, while the Chern number does not really matter, like how big your system is.
Right, because you're integrating over it, right?
Exactly.
Okay. Thank you.
Yeah. Very good questions. These are very important questions. So if you have, if you still have energy, we can now look at the problem of the lattice. I stopped it. Now, so far we just learned what happens in the continuum. Now I want to ask the question, what happens on a lattice? What about lattice? So I have magnetic field, but now my electrons are confined on a square lattice for simplicity. Okay. So the crucial point about the magnetic field was that if I have a magnetic field, remember R on a Bohm phase, is that if I have some magnetic field and my electron goes this way or that way, depending on the area around it, my electron will acquire a phase. In particular, if I go around this magnetic flux, if I go around the single magnetic flux, I just get 2 pi. If I go around a fraction of a magnetic flux, I just get 2 pi alpha, where alpha is some number from 0 to 1. Okay, so now when we have some magnetic field, let's say it's in plane or out of plane, and now my electrons are confined to these sites, then can have a situation that when I'm going around the lattice, I will acquire an alpha, which is 2 pi alpha. Okay, so when I put these electrons on a lattice, if you want, so it's the same Hamiltonian that we had before, that it's a uniform magnetic field plus some dynamics, but then I have a lattice structure, V of X and Y, and this V of X and Y it forms a lattice in 2D, such that my electrons wants to be at the bottom of this lattice. In principle, you can solve this problem. You remember when we have a lattice and we do the block theorem, and then we look at the Vanier functions, and we look at if it's a very, very deep lattice, what happens to that? We don't need to take care of all the other Vanier functions. What happens is just these these guys can hop from one side to the other side, and we write a tight binding model for this. Here is the same thing. I assume that the lattice is very, very deep, so electron cannot hop to other orbitals in these wells. It can only hop from this orbital to the same orbital to the same orbital on neighboring sites. So the very similar to just the 2D without magnetic field, I would like to write a tight binding model where my electrons are hopping either in the X or Y direction. And also this is X and Y. Plus A dagger hopping along the Y direction. A X, Y plus complex conjugate. So I assume a deep lattice. So then if you like the electronic wave function, the Vanier function is like this, but then it can hop either in the Y direction or on the X direction. Now, if I want this electron to feel the effective magnetic field, then I have to make sure that when it's hopping in the X direction, it would acquire some phase. And then when it hops in the Y direction, let's say I just don't give any phase. So when I'm hopping in the XY direction, in the Y direction, I don't want to get any phase. I want to add just phase when I'm hopping in the X direction. So if I just put 2 pi alpha over here, and say plus, and then minus 2 pi alpha when I hop backward, what happens? So first of all, there is a question. Okay, yeah, it's just good to continue. First of all, when I put this 2 pi alpha, I have to put minus 2 pi alpha over here. Why? What property of the Hamiltonian makes me to do that? The Hamiltonian should be Hermitian. So if I'm hopping from site A to site B, and it is accompanied with a phase, if the Hamiltonian wants to be Hermitian, then it should get the opposite phase, right? So since the Hamiltonian is Hermitian, then certainly when I'm going backwards, I should get the opposite phase. Now, if I put 2 pi alpha over here and then 2 pi alpha over here, is that enough? Let's see. If I go around the system like this, 2 pi alpha, then 2 pi alpha, then if I go, let's say, clockwise, here I get 2 pi alpha, here I get 0, 0, and then I get minus 2 pi alpha. So overall, I will get 0. If you do counterclockwise, you also get 0. So the trick that you have to do is that you have to put this phase to be row number dependent. You need to get some phase that is larger for when the row number increases. And now when you do this, it's y plus 1 and then y. Then if you calculate that, then you see that you get 2 pi alpha. So if I want to add now these parts into the Hamiltonian, is that I 2 pi alpha y, and the complex conjugate 2 pi alpha y. And over here it's just 0 e to the I0. Just ignore writing that. So I did not derive the Hamiltonian from first principle. If I wanted to do that, I should have, as I said over here, I should have started with the Hamiltonian, with the trapping potential and the magnetic field. But I kind of motivated why Hamiltonian of an electron hopping on a square lattice in the presence of magnetic field should look like something like this. So now, so this is exactly this is kind of called the piles substitution. Piles substitution. When you take your tunneling and then you replace it by IH, the vector field integrated over the link that connects site I and site J, if it's a tunneling between site I and site J. So we over here, if the let's say the A was in the Landau gauge minus BYX, then integral of, let's say, to x plus 1y would be minus by x dx in the x hat direction, and this is nothing but so minus by, and then the length of the system, the length over here, which is basically A. Sounds good? So basically, if another way to basically drive this Hamiltonian is to do this pi substitution, that when I'm hopping, I will accumulate some phase because of my magnetic field, because of my gauge field. And if I calculate this for the Landau gauge, I will recover the same value that you need to put into your tunneling time. So this is like another way of arriving at this Hamiltonian. So now the total magnetic field in the system is basically just accumulation of all these guys. So if I have nx and ny sites, each of them has a fraction of flux alpha. So that would be the total magnetic flux. Okay. And then alpha, as I said, is periodic. So alpha can go from alpha and alpha plus 1 are basically equivalent to each other. Sounds good? Now, this Hamiltonian is for electrons on a lattice with a non-zero magnetic field, but one can simulate the same Hamiltonian for photons, for atoms, for whatever, as long as you can engineer this phase to be something that increases with the number of rho. And if you do that, even if the particle is neutral, it feels the same Hamiltonian. So then it should be it should feel the same. It should feel the same kind of physics. It should experience the same dynamics.
Mohammed?
Yes.
But so you're constraining the system or to the wave function to acquire a phase 2 pi every time it makes a closed cycle. But I don't see, why is that necessary? What happens if the phase is 0, let's say, after a closed loop?
Over here,
How is that?
if the phase was 0, if 2 pi was 0.
Yes, yeah, to constrain the system to be 2 pi, then you sum up over y, right? But if you don't sum up over y, then in a closed loop, it will the total phase will be 0. But I don't see why is that problematic. That's what I don't understand.
I'm not sure that I got the question. So first of all, in order to simulate the effective magnetic field, or in order to capture the effective magnetic field, my electrons, when they go around a closed loop around each plaquette, they should acquire a non-zero phase.
Oh, so that's because of the magnetic field.
That's the Aharonov-Bohm phase, and the phase that I get around a closed loop is equal to the number of magnetic flux that I am encircling. If I'm encircling a fraction of the magnetic flux, then that would be a fraction of 2 pi. So if it's a single magnetic flux, then it's 2 pi. But if it's a fraction of magnetic flux, it would be 2 pi, that fraction. And I call that fraction alpha.
Okay, so regardless of the periodicity, if a particle in a magnetic field, every time it makes a loop, it acquires a 2 pi phase.
Exactly.
Okay, that was the question. Thank you.
Yes, yeah. So I did not, as I said, I did not derive this from first principle. If I really wanted to do that, I should have done the full problem. And actually, no one does this. Usually, the way that people do it is that they do this pile substitution. They say that when I'm tunneling on a lattice, I'm going from one side to the other side. If I'm in the presence of a non-zero gauge field, then I have to modify my tunneling by this expression. And then you immediately see that this is for one link. Imagine that I do this from here to here to here, and I go around the plaquette. Then the total phase that you acquire will be now I doesn't come. It would be E over H. Now the loop integral of A dot dl, right? If it's for a closed loop. And what is this? This is the magnetic flux divided by the magnetic flux quantum. So this will be phi divided by phi 0. Sounds good?
Yeah, thank you.
Yeah. I mean, ask questions, guys. I mean, if it's nothing. So one question before moving on with this lattice. At what value of alpha do you think we can recover the continuum model?
So if the magnetic length becomes the lattice constant scale, this will approximate the continuum.
Okay, indeed. So one can actually think of the magnetic length and then find what magnetic length is as a function of alpha. So you remember that magnetic field was proportional to 1 over square root b, and then b is now proportional to alpha. So it would be something like this. And then if this is, you have to consider some a over here. I didn't go through the details of it in particular to not make it complicated, but the lattice, let's say the lattice has some length scale a. So now if you do it correctly, then there will be an a that appears over here. Now, if your magnetic field is small, which means that if your LB is large, much larger than your lattice spacing, then in this limit, you expect that you recover the continuum model because your magnetic orbitals that are like this, and their length is LB, they're much larger than lattice spacing, so you don't see the lattice structure because your magnetic length encompasses many lattice sites. So So over here, which basically means that alpha is much, much smaller than 1, then this lattice is equivalent to continuum. Okay, so now what is the band structure of this Hamiltonian? One can, of course, numerically solve this, and Hofstadter actually did this in a long time ago. And then what he realized is that it would become something like this. So if I put the system on a torus, and then this is the energy, eigenenergies. This is the value of the magnetic field. Remember, the magnetic field was proportional to alpha, and alpha was periodic in 1. So goes from 0 to 1, and then after that it would repeat itself. So for any value of alpha, you can look at the energy eigenvalues. Then if you solve it on a torus, on a periodic boundary condition, you see the following, that you will get these magnetic bands. And then in between them, you don't have any energy, so these are the gap. These are the gap over here, and these are the gap over here. Okay? So now, if I look at now a system that is not on a torus, if I look at the system on a square, not on a periodic boundary condition, so this is a periodic boundary condition, but if I just look at the rectangle, let's say Lx and Ly, then apart from these states that you had in the past that were like this, you will see some states that appear between these bulk bands. And these are, if you look at the profile of them, if you look at either the current or the density of them, you see that they are confined around the edge of the system. While these guys are concentrated in the bulk of the system. So that's why you call these bulk states, and then you call them edge states. Okay? Now, what is interesting is that you have edge states that go counterclockwise, and then you have edge states that go clockwise. These are these ones and these ones, and they have opposite energy. You see, the energy of these are positive, the energy of these are negative. This is very similar to an electron in a magnetic field, right? That you have an electron in a magnetic field with different orbitals. That's the Hamiltonian of the system. That's the energy of an electron that has orbital angular momentum. So if the orbital angular momentum is aligned with the magnetic field, it has a lower energy. If it's anti-aligned, it has a higher energy. So this one, for example, this one is anti-aligned with the magnetic field, it has a higher energy. This one has the opposite orientation, it has lower energy. So it's very similar to a magnet in a magnetic field, because it's just orbital motion. So it's basically obvious that why the energy of this one and why the energy of this one are different from each other. Okay, so now what about the robustness? Imagine that I put some impurity over here. Then this guy, the electron or photon, wants to go, but it has a disorder over here. So naturally what happens is that it would go back scatter and then goes in the opposite direction. But if I want to back scatter and go in the opposite direction, that one has a different energy. It has a lower energy. So I have to pay an energy price, which is not usually allowed. So if I just want to do elastic scattering, and if the elastic scattering is not allowed, inelastic scattering is not allowed, I cannot go backwards. So instead what happens is that I would go around this impurity and then continue my way. So this is again another manifestation that I put my finger somewhere on the edge of the system, then the photon or electron will go around that impurity and then continues its way. So the basic physics here was that the edge states over here and the edge states over here, they have opposite energies. So far so good. Now one can build more intuition in this square lattice system, and this is using this magnetic plaquette. Imagine on each of these guys I acquire a phase alpha, and then alpha is some rational number. So it's some p and q, and then both of these guys are integer. Then if I assume a plaquette that has q sites, or if you look at supercell that has q cells, then the phase that I acquire when I go around it is 2 pi, right? Because it's 2 pi p, but p is an integer, so it doesn't really matter. 2 pi p and p are the same. So if I actually have these, if I hop on these magnetic cells that each of them has q in them, then it's as if there is no magnetic field. Does that make sense? Remember that the tight binding model, in a normal tight binding model, when there was no phase, you would hop from one side to another side and there was no phase, and then your energy was just 2j cosine kx and cosine ky. Now here, if you go into those plaquettes, if you think of those q plaquettes, then they would hop with non-zero with zero phase. So if I had then basically what you have is that you will have q bands, and each of them will have nx and y over q states, because basically if I go to each of those if I can have this plaquette that has q sides, and then when it's hopping, it's just a simple tight binding model. So for each of these q bands, the problem reduces it to a tight binding model, where each of those tight binding model have these many states. So over here, for example, for alpha 1/3, you will have 3 bands, and then each of them will have nx and y over 3 states. Okay. So now this is the story of a particle on a lattice. Now, if you understand this well, and if there are no questions, we can do this for photons. If you can simulate this Hamiltonian.
So I have a small quick question.
Sure.
So you just said the energy is just like what we have of a dipole in a magnetic field, you know, the B dot L stuff. So is it true that if we cut the area in half on the right, you know, that blue round, so if we cut that in half, then the energy will be cut in half?
If we cut what in half?
Yeah, I mean that kind of diagram you draw, the blue lines that goes around the impurity, that's that picture. So is there essentially a photonic dipole here? I mean, so that means if we have enough impurities, we cut that lattice area in half, and so the energy will be in half. Is that true?
Sorry, I'm not following. Is that you're saying that if I have this guy, if I like cut the system in half?
Yes.
No, the energy of the system does not have any size dependence. So you see in this Hofstadter butterfly, it's actually an interesting question. So over here, when I'm looking at the energy spectrum of the system, there is only one parameter, alpha.
Yeah.
And there is this J, the units, E in units of J. There is no NX and NY in it. The system does not enter into my calculation.
Oh, yes. So
similar,
okay.
Just let me a second. So similar in a tight binding model, when you just with no magnetic field, if I just have a particle that hops on a system, then there is no system size in it.
Yeah, okay. So I ask this because I was thinking, you know, that the energy, if we make this comparison to the okay, never mind. Okay, I understand it. Thank you.
No, sure. Any other question? No question? Okay, so now we are at the photons, and then we come back to it later. So now I want to do the same Hamiltonian. I want to simulate it for photons on a lattice. I want to simulate that alpha for photons on a lattice. How can I do that? So if I have two resonators that are coupled to each other, it's the left resonator and the right resonator, then in the second quantized form, it can be described by AL minus AR minus AR. You can write it either in terms of Hamiltonian, or you can write it in the couple mode theory. Couple mode theory, which basically works very well for non-interacting systems, and they're equivalent. Either you write a Hamiltonian description of the system or coupled mode theory, they are the same. So in that one, you have AL T A R T, and now this AL, if I want this in the classical physics, that will be the amplitude of your electric field. So this will be the amplitude of electric field in resonator left and resonator right, and you will get this. In order to couple it related to the quantum mechanics is basically assuming that you have coherent state in each of them. So AL is nothing but the expectation value of this operator in that resonator, and AR, the expectation value of A in that resonator. So for coherent state, you see that this is just obvious. So as long as you have no interaction in the system and the state remains coherent, then these two descriptions, this Hamiltonian and coupled mode theory, is just exactly the same thing for non-interacting. You can convince yourself by writing the Heisenberg equation of motion for these ones. So AL, let's say, is IHAL, and then this gives you plus or minus, it doesn't matter, R, and these are operator. Okay. Now, what we want to put some phase over here. That's all we wanted, that we learned from the previous discussion, that we want to put some phase in between. In order to do that, we can do some trick, and that's what we are gonna study in the next like 10 minutes. Okay, so what we want to do, we want to take one resonator here and one resonator here, and we want to put a cucumber or a Mickey Mouse, or I don't know, a Dumbo or whatever in between. So you have one resonator, left resonator here, one other resonator here, and I put another resonator that is anti-resonant. What do I mean by anti-resonant? It means that if the perimeter of the left and right resonator is some m integer times lambda, and this is m lambda, I want this one to be m lambda plus lambda over 2. Lambda is the resonant wavelength at which I'm interested to study the system. Sounds good? Now, why do I want to do this? I want to do this such that if the photon is resonant over here and it's circulating like this, circulate like that, and then it can get scattered and then go into the other resonator. I want this photon to get scattered to this middle one, but I don't want it to spend time and then go around the circle. I just want this one to hop once, so it comes over here, it scatters, and instead of going all the way, it would hop into the other resonator and then continues to circulate. And then once it comes back, again, it's scattered in this two waveguides that are close to each other, then it would go to the top resonator, to the top part of the resonator, and comes back to this one. So when I'm hopping from left to right, I will take the lower path. When I'm coming from right to left, I take the upper path. Because of this anti-resonancy condition, I don't circulate in the middle guy. I just hop either from here to here or from here to here. Now, if I put this resonator asymmetric, basically as I've shown over here, then the optical path that I take when I'm going from left to right is different from the optical path when I go from right to left. So when I'm coming from here, I'll take this path. When I go from right to left, I take this path. If the optical paths are different, then I accumulate a phase that is different when I go to left to right. And then that's basically gives me the phase that I'm looking for. In order to get this and formalize this, I have two options. I can either use this coupled mode theory, or I can use transfer matrix formalism. Here I just use that coupled mode theory because it's a little bit easier. But I suggest that you go and do the transfer matrix theory. Okay, so in the coupled mode theory, if I have a resonator that is coupled to a waveguide, this is A, and then coupled to a waveguide, this is E input and E output. And this is this is coupled with some rate kappa. Then this mode decays at a rate kappa, so the amplitude will decay exponentially as a function of time. So this makes sense. And it's getting filled up by the electric field input that is coming from the left. So this guy goes inside, but then it leaks out. So A is getting depleted, but then at the same time getting replenished by the field that is coming in the input. Another condition is just the boundary condition. The electric field on this side and the electric field on this side should be related to each other. This is just the Maxwell's boundary condition. So this E out should be E in plus 2 kappa A. This is also so-called input output formalism. Now, I have to, what I need to do is to use these equations a couple of times for once the left resonator, the right resonator, and then assume that the light propagates freely in the middle waveguide over here, and also propagates freely for the middle guide over here. So if I if I annotate these fields at A in left, A in left, A out left, over here it's A in right, and A out right. Now I have to write a bunch of equations and then solve them. Then I don't do it right now. You can look at the notes. In particular, if you look at this one. So now I have to write for the left resonator and right resonator, they both decay and they have their corresponding input field. They have their boundary conditions that I just described previously. But on top of that, we have this propagation. Oops. We have this propagation that over here, the E out will propagate and accumulate some phase depending on the length of this resonator that I have chosen it to be this. And then over here, I take an accumulated phase that I have it chosen to be this. This is the optical path phase that I acquire. So when I go from one side to the other side, I will acquire some phase that I just showed over here. And then for the other path, I will have over here. If you solve these equations, then you can convince yourself that the equations of motion that corresponds to this will be basically effectively two resonators that are coupled to each other, and they have this phase that we were looking for. So if I now look at the Heisenberg equation of motion for this H, it would give me these things if I eliminate these EL ones. I'm not interested what happens to the E in and E out, because this one is basically off resonant. I'm not interested in the dynamics of the photon. I'm just interested in how the photon is hopping from this side to this side. And then that would be the effective Hamiltonian that I have for the system. So now I just fast forward. Now, once you have this kind of Hamiltonian and you know that you can tune the phase with this asymmetric phase shift that you have from the upper path and the lower path, then you can tile your system. And this would be one resonator, another resonator, another resonator. Then you tile it with these resonators that are shifted with respect to each other, such that you get a 2 pi alpha phase around each bracket. I make a two-dimensional array of these ring resonators. In particular, I will make resonators like this and resonators like that. And then I couple them with the resonators that are asymmetric. But I couple them in such a way that when I go around a single placket, I get 2 pi alpha phase. Now, if I do that, then I know by all the discussions that we had, the spectrum of the system will be Hofstadter butterfly, etc., etc. So I would like to stop over here, answer some questions, and then in the next round, we will look at into more detail what's the experimental implementation of this thing would look like, and what are the physical observables for photons, and then the other models that we just advertised that are more relevant for photonic crystals.